students, we are studying what now? Examples of tunneling effect. Okay, one example we have studied in the last video lecture, that is alpha decay, and now this is second example of tunneling effect, that is tunnel diode. Tunnel diode is what? Tunnel diode is a simple PN junction diode, but there is a little bit difference between normal PN junction diode and tunnel diode. If you see normal PN junction diode, P-type semiconductor is connected to N-type semiconductor. You know, P-type semiconductor, here majority charge carriers are holes and here majority charge carriers are electrons. Now once the junction is formed, electrons move towards P region and holes moves towards what? N region. So that depletion layer is formed here. Depletion layer gives rise to what? Potential barrier. Now because of this potential barrier, now these electrons cannot move towards P region. This depletion layer acts as a what? Potential barrier. So electrons cannot cross this depletion layer and they will not move towards P region. Now since electrons are not moving, that means current will not flow through the diode. Now how these electrons they are made to flow from N region to P region? Again, we have to increase the energy of electrons. If electrons energy becomes greater than potential barrier, then it can overcome that potential barrier and it can move towards P region. So to increase energy of electron, we have to apply what? Forward bias. Now because of this forward biasing, electrons energy increases, and now once electrons energy becomes greater than potential barrier, it can cross that depletion layer and current flows to the diode. So these characteristics we can show in the graph. This IV characteristics of normal PN junction diode. You can see here, initially current flowing through the diode is very less, because here this potential means applied potential or energy of electron is less than what? Potential barrier. So in this region, electrons energy is less than potential barrier, but here the applied potential becomes greater than potential barrier. You know, for silicon it is 0.7 volt. So when applied potential becomes greater than potential barrier, electrons can overcome the potential barrier and they can move towards P region and current flows to the diode. So from here onwards, the potential becomes greater than potential barrier and current increases. So in normal PN junction diode, until electrons energy or until applied voltage becomes greater than potential barrier, current is very less. You can see here, no current, almost no current is there. Almost current is zero here. This is normal PN junction diode. But what happens in tunnel diode? Tunnel diode, as I told you, it is a simple PN junction diode. But what is the difference between these two? In tunnel diode, P and N type semiconductors, these two P and N type semiconductors, they are very heavily doped. Concentration of dopants is very high. So they are very heavily doped, means large number of holes are there in P type region and large number of electrons are there in N region. So because of heavily doping, what happens? Width of depletion layer becomes very thin, about 1 nanometer, and here depletion layer is acting actually what? Potential barrier. But in tunnel diode, the layer of this potential barrier or layer of this width of depletion layer is very small. So because of thin depletion layer, even though the potential is less than potential barrier, this applied potential is less than potential barrier, since this layer is very thin, these electrons can directly cross, means these electrons can directly move towards P region, from N to P region. So here we can say that electrons tunnel through the potential barrier. The electrons can tunnel through the depletion layer and they come towards P region. So current flows to the diode, you can see here. So in this region, the applied voltage is less than potential barrier, still current is flowing. So here you can see the difference between normal PN junction diode and tunnel diode. You can see here, current is almost zero when applied potential is less than potential barrier. But here, applied potential is less than potential barrier, but still current is flowing. Now this current is due to what? Tunneling of these electrons from P region to N region. Right now, electrons are having less energy to overcome this potential barrier, but they can tunnel because the electrons are considered as what? Wave. According to quantum mechanics, matter waves are associated with these electrons. So those waves means electrons can tunnel, can penetrate through the potential barrier and current increases. So this current is called as what? Tunneling current. In this way, tunneling effect is used in tunnel diode. Now further characteristics, our interest is here only, but if you want to know the further characteristics are like this. Further, as you increase the voltage, what happens? The misalignment of this energy band takes place. Misalignment, because of this misalignment, now further current decreases, and again, from here now the applied voltage becomes greater than potential barrier. V becomes greater than VB. So once potential becomes greater than VB, it acts as a normal diode and current increases. So from here onwards it acts as a normal diode, but here it is what? It is the characteristics. This is special characteristics of tunnel diode. So in this way tunneling effect is used in tunnel diode. Tunnel diodes are used for fast switching devices because of these characteristics. All of you got it? Tunnel diode, tunneling effect in tunnel diode. Okay, now the next example of tunneling effect we are going to study is what? Scanning tunneling microscope. This is one more example of tunneling effect. Now microscope, all of you know, microscope is used for what purpose? To see magnified images of the objects. Okay. Now scanning tunneling microscope, it is we know there are two types of microscopes. One is optical microscope where light is used as a source, and electron microscope. Electron microscope where electron beam is used as a source. So electron microscopes are having what? Higher resolution than optical microscopes. So scanning tunneling microscope, in short we say STM. It is a non-optical microscope. It is electron based microscope, and these are generally used, STMs are used for what purpose? To study images of surfaces. To study what? Images of the surfaces at the atomic level. Means how the atoms are arranged on the surface of the specimen. It can be studied by using what? STM. So such a high resolution is there. So how tunneling effect is used here, that we have to see only. So we are not going to study in detail of STM working. We are just studying what? Principle of STM, means how tunneling effect is used here. Okay. So this is basic block diagram of tunnel STM. You can see here this is sample whose image is to be formed, surface image is to be formed, and this is STM, various parts of the scanning tunneling microscope. This is tip, it is called as conducting tip. It has sharp tip, it's called as conducting tip, and it is connected to this probe. So this probe is used to move this tip on entire surface of the specimen, so that entire surface of the specimen will be scanned. Then current, whatever current is produced here, that current is very small, so that current is amplified by using what? Current amplifier. It is given to control unit, and then from there current variations are given to data processing unit, where the data is processed and image of the surface is displayed on the screen. So this is basic block diagram of what? STM. Now see how tunneling of electrons occurs here. Because of tunneling effect, small electric current is produced in this device. So see what is done here. This tip, scanning, it is called a scanning tip. This tip, conducting tip or scanning tip, it is brought very close to the surface of the specimen. It is not touched to the surface of the specimen. Some gap is kept between tip and the specimen, but that gap is very, very small, around 1 nanometer. Such a gap is there, and small bias voltage is applied between what? Tip and the sample. Suppose tip is given positive potential and the sample is having negative potential, but that is very, very small. So small biasing potential is applied across tip and the sample, and there is a small gap between what? Tip and the surface of the specimen. So can you tell me if we are applying, suppose here, positive potential, so can electrons which are present on the surface of the sample, can those electrons will attract towards positive potential, and they will penetrate, means they will flow through this probe, through this tip and this device? It is actually not possible, because no electrical contact is there between tip and the sample. Small gap is there between tip and the sample. No electric wire is connected between them. So that gap acts as a what? Barrier here. because of that gap, because of that barrier, the electrons cannot, we can say electrons cannot leave the surface of the sample. The electrons are not permitted to leave the surface of the sample because biasing potential is very less. So what is our expectation? Ki no current will flow through this device. But according to quantum mechanics, as we know, tunneling can occur. Means you can see here, this is surface, electrons on the surface of the sample, and these are the electrons which are present in the tip of the probe. So, and this is the gap between these two. So according to quantum mechanics, matter waves are associated with these electrons. So even though the gap is there, even though the barrier is there, these electrons can tunnel through this barrier because they are considered as what? Wave. So the wave can tunnel, means electrons can tunnel through this barrier, and these electrons can move towards the tip of the probe, and the flow of current takes place here, and that current is amplified by the current amplifier. So in this way, tunneling effect occurs in STM. Okay. Now as the tip scans entire surface of the specimen, you know surface geometry is not uniform. It will be like this. So somewhere current would be less, somewhere current is greater, and so on. Where the distance is less, current is greater. Where distance is less, current is greater. Where distance between the tip and the sample is greater, current is less. In this way, so current variation takes place as this tip scans entire surface of the sample, and this current variation is recorded to form image of the surface of the sample. So in this way, STM is used for imaging surfaces at the atomic level. So all of you got it, tunneling effect, how tunneling effect is used in STM. Okay, so these three are examples of what? Tunneling effect, alpha decay, then tunnel diode, and STM. But you have to write the answers of these questions in very short, because this is only 4 marks question. So you have to write statement of quantum mechanical tunneling effect, and then you have to write principle of tunneling effect in STM in short. So you can refer the notes for this. Okay, so here our third unit is completed. Only numericals are remaining. So in the next video lecture we are going to take what? Numericals based on wave equations.